So you want to factor x to the fourth plus 1. Well, to do that, let's first look at the equation x to the fourth plus 1 is equal to 0, and we'll try and find the roots of this and use that to factor. Right, so subtract 1 from both sides, and those roots to that equation end up looking like this. R1 is equal to root 2 over 2 plus root 2 over 2i, and R2, R3, and R4 are going to be in the same places in their respective quadrants in the complex plane, if that makes sense. Now, one way to find these roots is to convert to polar coordinates, actually. So we have x to the fourth is equal to e to the I pi, right? Because negative 1 is equal to e to the I pi. And then we take the fourth root of both sides. And remember, when we take the fourth root of a complex number, you have to account for the possible multiple roots that we have. All right, so here k could be equal to 0, which would correspond to R1, or it could equal 1, 2, or 3. So if k equals 0, 1, 2, or 3, then we have R1, R2, R3, or R4. Now, by the fundamental theorem of algebra, we can now factor this polynomial as this: x minus r1 times x minus r2 times x minus r3 times x minus r4. And actually, the coefficient in front of the x is the same in both of these, so we are a-okay. We don't need to worry about a single thing. Now, if you'll notice, each of these r's are complex numbers, and when we factor, it's nice to have real coefficients. So in order to do that, we'll see that something really nice happens if we group these together. Now, I prefer to group the first and the last together and the middle too, but you could also do these two, and that would work just fine. If you end up filling that out, this is what you get for the first and last, and this is what you get for the middle two. And now, when you plug in the values of R1, R2, R3, and R4 from earlier, you'll find that this is the factorization that you get. So there you go.